So last night I learned with my kids that the fastest onion ever eaten raw was devoured by Yusuke Yamaguchi from a Japanese person, and the process took a little bit less than 30 seconds, so 29.5 seconds. And today I will try my best to teach you something equally interesting, so I will hopefully be able to teach you a little bit about Michelson interferometers. So I will speak a little bit about the Michelson interferometer as an instrument, and as the usual thing goes, I will derive the conditions of calculating the phase differences for a light propagating or two rays propagating through the different arms of the interferometer, and then subsequently we can understand how interference patterns are being formed or fringes as a function of changing the mirror separation. And then in the second part, I will show that how these kind of Michelson interferometers could be also used as a spectrometers, which is quite neat. It's quite nice, especially because there we are able to see that we can take use of the Fourier transform magic in order to do something useful related to the physics and chemistry. And then finally, I will speak a little bit about the kind of how we can generalize or improve the Michelson interferometer, the simple configuration, so that it would be workable in a more realistic settings and practical settings, especially when we are using incoherent broadband sources, as we commonly are when we are using these kind of interferometers. And for example, performing Fourier transform infrared spectroscopy, FTIR spectroscopy, using interferometers. So this is what I will be speaking today, and I will get started right away. So I will introduce to you how a Michelson interferometer works, and especially it is firmly motivated by the fact that the Michelson-Morley experiment was used to unravel the speed of light, if I recall correctly. And this is the schematic how the Michelson interferometer looks like. So essentially, we have two mirrors here. A beam of light is arriving into a beam splitter at this point A. It reflects into the second mirror, and an optical path length of light is associated with this propagation. And then the second beam of ray of light goes through the beam splitter and into the detector. And similarly, here the original single ray of light is being split into two, and there the first ray of light is hitting the mirror 1, being reflected, and then reflected again at the front surface of the beam splitter, and then being propagated into the detector. And here we are calculating the superposition fields of these two rays, so 1 and 2, and this is where the interference fringes will be detected essentially with the detector. And Michelson interferometer, it has huge number of applications in practice, and I guess maybe the first one that comes to my mind is the FTIR spectrometers that can be realized using these interferometers. And they are very handy if you want to measure some spectra of the IR wavelength region of some molecules and samples, and you want to do that with the good precision and accuracy. So the beam splitter here, it's essentially a so-called 50-50 beam splitter. So 50% of the beam splitter's input beam will be reflected right away, and 50% will be transmitted. So that's what the notation of 50-50 inside the parentheses essentially means. And of course, you could imagine that we could have also other kinds of beam splitters. So we could have, for example, 10-90 beam splitters, where, for example, 10% of light is being reflected and 90% of light is being transmitted. So depending on the application, of course, we can have all sorts of different kinds of beam splitters. And there, I would point out that in the possible case you're wondering how we could even realize these kind of more arbitrary beam splitters with the arbitrary splitting ratio. Of course, one could realize them by just using thin film structures, where one could really design the Fresnel coefficient to be correct, or one could also just use two prisms hold together, having a slight air slit between the two prisms, and then controlling the distance between the prisms, we could control the transmittance and reflectance ratios. But more on those, I think, if I recall correctly, in the homework exercises. So we have two mirrors, and we denote them in the figure as M1 and M2, and of course we have a detector. And what we are then measuring is that we are measuring an interference pattern, and that is changing while we are changing the mirror positions. In practice, we only need to change the one mirror position here, because it's really only the difference in the optical path lengths. The different rays accumulate, or the phase accumulation due to the different path lengths, so that we do not need to change both of the mirror positions, but rather just one. But that one we need to adjust quite accurately. And here we are essentially just changing the phase accumulation by changing the optical path lengths, like I just said. And now we're using a 50-50 beam splitter. So like I said, 50% of the incident light can be made to interfere with the detector. And this is the downside that we have in the Michelson interferometer. I did not draw it here, but let me clarify by just pointing out with this arrow. So if the 50% of light is being reflected here, then everything will be reflected here, and then my second ray of light is hitting the beam splitter again. So only 50% of light is actually now being transmitted into the detector, and 50% is being reflected back into the original direction from which the beam came from. So we are losing already 50% of the second ray of light. And then, 50% of the ray 1 gets through and then forms the ray 1. And then here another reflection takes place. And lo and behold, not all of the ray 1 actually is being guided into the detector. But again, 50% actually is being transmitted through the beam splitter. And that's why we are losing quite a bit of light in this configuration. But this is unavoidable, so there's nothing we can really do about it. It's just that how this kind of interferometer works. So let's denote the separations of mirrors from the beam splitter as D1 and D2. So these would be the mirror distances from the point A as shown in the figure. So that's a location on the first interface of the beam splitter. And the path difference then between the two different rays that they are seeing at the detector, the big lambda, the delta looking sign there, that essentially is 2 times the difference between D2 and D1. So essentially, physically, we are having a ray propagating this distance of D2 twice, since it's being reflected, and the same thing for the D1 here, so that in overall the phase difference that is being accumulated is then associated with this path difference of big lambda here. Of course, the path difference the phase difference we get by multiplying with k. So let's denote this so that the difference in d's is just d, and then we can work out the rest of the math for the phase difference. And let's assume now that the mirrors are identical, so that if there's any possible phase differences due to the reflections, they will be same for both rays, so we do not need to consider those. And if we take into account the fact that we have either plus minus pi phase shift caused by the beam splitter, so essentially the reflection there, then the overall phase difference becomes of a form that we have the delta, and that's equals the amplitude of the wave number k times big lambda plus minus pi. And let me stop now and just say here that, where do we get this strange plus minus pi phase shift here caused by the beam splitter? Essentially, we are getting that when a ray of light is being reflected, and that will give an additional phase shift. If you smart people there are actually listening that, hey, in the chapter regarding propagation, recalling Fresnel's coefficients, these phase shifts actually dependent on the input polarization. You are exactly right. So actually, we only have a phase shift in reflection for a given polarization component. I'm sorry, I do not remember by heart which one it is. Was it like for the polarization oscillating either perpendicular or parallel to the plane of incidence? But either way, there is a phase shift when we are coming into an air glass or air medium interface. And now, interestingly enough, similar kind of phase shift actually takes place when we change the polarization and now also change the media of interest. So now when we are coming actually from here, we are coming from the optically more dense medium, so from the beam splitter into the beam splitter air interface. And here we will then also have a same kind of phase shift for the other orthogonal polarization component. So in overall, we do have this kind of one phase shift for both of these polarization components. If you do not believe me, please look it yourself from the earlier chapter or from the booklet, and you know that it is the truth I'm speaking here. And now we can actually calculate the actual phase shift, phase difference, delta, and that's of course 2 pi divided by vacuum wavelength lambda naught times 2d. So we just insert the big lambda there, and then we have the plus minus pi. So this is basically, we can multiply the 2 into the 2 pi, so we get this kind of relation here for the phase difference delta. And now, okay, this essentially tells us that when we have this phase difference and when it is an integer of 2 pi, so essentially delta equals 2 pi m, where m is an integer, we have constructive interference. So we will have a maxima in our interference pattern. And this gives us an equation so that we have the 2 pi m equals delta. And then we can solve this with respect to the d parameter, which is essentially the difference in the optical path lengths. And this gets a form that we have 2 times m plus 1, m is an integer, times lambda naught, so the vacuum wavelength divided by 4, and we can simplify this into a slightly different form, where we have the m as a single integer, not multiplied by 2. And of course, same way, destructive interference takes place when the phase difference is an integer of 1 pi, so we have interference minima, and then we have a similar kind of condition that we can calculate, that the d then should be m times lambda divided by 2. And now we can right away calculate what is the difference between the maxima and minima, and this difference then essentially is the lambda naught divided by 2. So this is roughly giving us, interestingly enough, a means to allow estimate how precisely we need to be able to move our mirror so that we can see interference fringes. So we definitely need to be able to move things way more accurately than lambda over 2, because this is the separation between the subsequent maxima and minima, so the nearest maxima and minima. So we definitely need to be able to move things in a kind of pretty precise manner. So in a kind of the order of a few nanometers, 5 nanometers, 10 nanometers, that would be the required precision for moving the mirror. Of course, that can be done with the piezo devices, especially if you operate them with a closed loop configuration, no trouble there. But you do need to be careful when you're doing things, so that it's not entirely trivial anymore. For example, slight deviations in the temperatures will start changing the behavior of the piezos and their kind of assumed position a piezo motor actually has. Now, okay, let's think what we can now do with a Michelson interferometer. It has many applications, and the one I'm going to be highlighting here and providing you an example is that we can also use that as a spectrometer. And spectrometers are nice because we can use them to measure the spectra of light, and especially we can do spectroscopy by letting light to propagate through an unknown sample we do not really know that much about. So let's go through this example. This is a very neat piece of physics and math, I would say. So that's why I chose that. So we are interested in considering an interference pattern. And let's start by just considering an interference pattern created by using monochromatic light source. So we will soon generalize into a broadband light source. That's what we're actually using in a real spectrometer. But let's start with a monochromatic light source. So then we are actually measuring an interference pattern, so irradiance pattern, as a function of phase difference delta. And this is essentially of a form. We have some kind of like constant value to IO naught there, and then we have the actual interference pattern that is caused by the deviations in the phase difference. So essentially moving the mirror, one mirror in the Michelson interferometer, changing the optical path lengths, and then we are actually seeing a interference patterns formation. And here the phase difference delta, we can simply calculate it as before. It's exactly the same thing, so k times big lambda, and this is the same as we had before. And now I'll just change notation slightly, so I will write the inverse of lambda naught as a new tilde here. So essentially this is the spectroscopist's notation for a wave number. So it's essentially just 1 over lambda naught, so that we can appreciate better that we're actually trying to do spectroscopy here. So this is essentially what I do. And now we are ready to generalize our treatment to a broadband source. And now we are thinking that our broadband source has some given kind of irradiance distribution, irradiance here, and then this is a function of frequencies. So this is what we are now thinking. And what we are doing with this kind of broadband source, we are actually shining this into our unknown sample, and then we are measuring how much of light is getting transmitted through the sample. So let's assume further that the light then passes through a partially transmitting sample. This is the sample we do not know. We want to measure its spectrum. So what kind of frequencies of light are being absorbed, for example, into the sample, and what are fully just transmitted. And in this case, when we have this kind of partially transmitting sample, then the actual irradiance pattern when the broadband source has been propagating through the sample now, and that we would be measuring at the interferometer, would be a function of both d, the difference in the optical path lengths of the interferometer, and then of a frequency. Looks awful now, but it's not that complicated in the end. So I will first type down the math, and then I will explain what's happening here. So please remember, in the original slide, I had my irradiance distribution for a given frequency as a function of delta. And essentially, as a function of delta, it just means as a function of d. And that had a form that we had 2 times I naught plus a cosine of 2 times I naught here. So this is exactly what we still have. And only thing we have changed is that we have multiplied this original irradiance distribution with a transmittance function associated with our sample. So this big T S, as in sample, essentially it just tells us of how much of light of a given frequency, so a given wave number, is being transmitted through the sample. So this is a value between unity and 0, telling us of how much of the sample actually is being blocking different frequency components. And this first term that is not giving rise to interference pattern is being modified, and equally well, the one that is being modified is also modified with the transmittance function associated with the sample. And now this guy, of course, is of this form. Nothing strange there. We can just simplify notation that we just write this first term simply as an IS. So that somehow like the irradiance associated with the non-interfering path or part of the ray. And then we have we can take these 2 terms, and we all 3 terms. Also the coefficient 2 should be included here, and then we have an IS here. And this is exactly the same thing here. So we can just simplify the notation to make the math easier in the next slides. And now, okay, this is where we apply next the superposition principle. And this applies as long as we're in the linear regime, and we pretty much always are when we are doing these experiments. The detector that we have in the interferometer, essentially it just measures the total sum of the frequency components. So it really just measures the total irradiance associated with the incident light, and it doesn't really care about the actual frequencies. And mathematically, that just means that the measured quantity is the total irradiance as a function of d, or as a function of separation difference between the mirror position. And this is essentially, we are summing all different frequency components. So essentially, this is what we are measuring with our detector with the interferometer. So we are summing all different frequency components together, and this is essentially application of superposition principle into our physical problem. And now we can, of course, write what this I in irradiance pattern is. Then we have this kind of integral there. And let me now progress a little bit further to show you the whole beautiful thing, that how we can use this as a spectrometer. So we have the irradiance pattern that we are measuring, and this is a constant term. So in fact, we do not even need to worry about it too much. And this term is let me denote that as an I prime. This is the interference term. So this I prime, this is a function of the mirror position, and it looks like this. So we have an integral of some kind of term, which is a function of the variable that we are integrating over, and this is our integration kernel here, cosine of something. And if you are already familiar with the Fourier transforms, then you might be able to already notice that this integral actually looks like an inverse Fourier cosine transform of some given function. So essentially it looks that we are actually dealing with the math that we can write a time varying function using a Fourier cosine transform. So this is essentially, inverse Fourier cosine transform, so that we have a Fourier transform of my function f here, and then I'm integrating that with an integral kernel of cosine 2 pi variable times t, and then I'm integrating the different frequencies over. So here, capital F is the Fourier cosine transform of ft, a time varying function. And now we can equate really that these look exactly like this. And what this means is that really physically with these kind of devices, we can really measure if we measure the interferogram, so that ID function, so essentially we are measuring irradiance of light as a function of this D parameter. So essentially we are detecting light for a given mirror position. We measure the irradiance and we record the value. Then we move the mirror slightly, and then we record the changed irradiance pattern. And then we are moving even more slightly the mirror position, and we are again measuring the irradiance pattern. And this is how we can physically measure this thing known as the interferogram. And why it's called interferogram, it's essentially an interference pattern. And with that, what we can do is that we can now get information of the actual transmitted spectrum TS of the sample, simply by just calculating the Fourier transform of our interferogram. So that we can really then, we can measure this. Essentially we measure this with the constant term, but that can be easily gotten rid of. And then when we then take the Fourier transform, we can actually get the original object we wanted to measure, and that is the sample's transmitted spectrum TS. And this is super nice. So we can actually use Michelson interferometer as a spectrometer, which is not very clear when we start thinking about it, but in fact we can actually do that by just performing some Fourier magic. And the nice thing why there are devices known as FTIR spectrometers, so Fourier transform infrared spectrometers, is that by doing measurement using this, we can actually reduce the amount of noise quite substantially, especially when we are operating at the longer wavelengths. And when we are trying to measure light at the longer wavelengths, hence the IR part in the FTIR, the detectors that can be used are inherently quite noisy. And if you would be using a normal spectrometer based on, for example, a diffraction grating, we would need to use a camera or line camera as a detector. So we would actually essentially have many pixels, and we would measure with each pixel a different frequency component of light. And this way, when we are measuring, we actually are getting a lot of noise because of the fact that the detectors at those wavelengths, IR wavelengths, are quite noisy. But here, when we are measuring an interferogram, we can actually use a bucket detector, and we do not need to use a camera, and that can be used in essence to actually remove the amount of noise or reduce the amount of noise of the spectral information content quite a bit. And this is the main thing why FTIR spectrometers are used that extensively by people. So this is, of course, not entirely trivial, but this is the reason actually why FTIR spectrometers are used. It's not the fact that it would be super easy to use these kind of devices. They are not very cheap devices, but you can actually do better measurements using them. And now let's finally go through a little bit of further physics regarding the actual Michelson interferometer, and let's consider further of the properties that are associated with this kind of instrumentation. So how we can generalize things is that we can also use a camera as our detector, And in this case, we are not just measuring a one ray of light, but rather we can measure the distribution of light. And this essentially just means that we can measure light that doesn't arrive into the detector or into the actual interferometer along the optical axis. So then essentially the path difference d, that we can replace that with a term d times cosine of theta. And this in practice means that we could even keep the mirrors both still if we change the angle theta. So essentially this would be the change here, and this could be done to kind of simplify things slightly. But I do not think I remember that the actual devices would be using this kind of possibility, but rather usually it's still the moving mirror that has been used. But at least this would be a possibility that how things could be generalized. Another possibility is, or the kind of, maybe let me rephrase, the trouble that we have with the first configuration we have shown is that it doesn't work very well when we have incoherent broadband sources. So this arises from the fact that the arms of the instrument actually are different. I will show pictures slightly soon in the next slide. and when the instrument arms are not identical, then interference is actually being reduced between the ray 1 and ray 2, and this degrades the performance of the instrument. And this is a downside of the first simplest possible scenario, how we can build a Michelson interferometer like this. And this is the downside of the simple configuration. So here, in this traditional configuration, the ray 2 transmits the beam splitter once, but the ray 1 actually transmits 3 times. So looking at the mirror, let me verify this. Okay, the ray 2 hits the beam splitter and is being reflected at the point A, and then goes through into the mirror M2, and then is being transmitted through the beam splitter once when it hits the detector. And then the ray 1 is coming, it's going through the beam splitter once, being reflected by the mirror 1, then second time, and then the third time propagation through the beam splitter before it hits the detector. So this is exactly the case, and this is something that can be, although improved. So we can really fix this situation by just flipping the beam splitter around and by adding a compensator plate that essentially looks like the beam splitter, and that we can then use to improve the coherence properties of the interferometer. So here, note, now the beam splitter, we have the 50-50 reflecting surface as the second interface, and now we have an extended source here coming, and then the light is being transmitted. The ray 2 is being transmitted once and then twice through the beam splitter, then it hits the mirror, is being reflected the wavefront, and then the third time it goes through and into the screen or into the detector. And this is, by the way, a possibility that if you have these kind of extended sources, then we could also have a screen or a camera here, and then we could get more information of the d times cosine theta term here. And then the ray 1, it's propagating through the beam splitter once, then it propagates through the compensator, and this compensator essentially it's like the beam splitter behaving like that, and the ray propagates once, reflects, and then propagates the third time through something that looks awfully like the beam splitter, or essentially looks like the beam splitter, and then finally is being guided into the screen and gives rise to the interference pattern essentially between the ray 1 and ray 2. So this is how things can be improved, and now the arms should ideally be identical, and this maximizes the spatial coherence of my configuration. And please note here, I'm actually speaking of spatial coherence here, so that this is what helps when I'm actually having an extended source here. I don't have the details or time to explain through the details of how this is the case, but this is a practical improvement that is being done. So if you want to understand more, please ask me, or even better, ask Jan or Madonna or Jussi or anybody else associated with the course of the further details that how come we need to improve the spatial coherence and what exactly this means. But this is the usual trick that can be done. And then, of course, we could use lenses as shown in the configuration here to adjust the angle theta so that we could also just change things with that. So essentially that would be an additional control knob of adjusting the phase accumulation and how the irradiance pattern is being formed. So this is what I wanted to say, 30 minutes about Michelson interferometers. I hope you found this lecture a useful one. And next I will be speaking about multiple beam interference. So essentially I will show that the somewhat similar kind of physics can also take place in thin film structures, where we are now in purpose actually increasing reflectivities of the thin film. But more on that, of course, in the next lecture. So thank you for listening, and good morning, good day, good evening, good night to you. Bye.